for reminding. Yeah, thank you for here. So, right. So the momentum is of an object is its mass multiplied by its velocity. So it's going to be a vector. And then we said about the center of mass coordinate. We know how to define the center of mass coordinate. Then we, by dividing by the time, we also get an expression for the center of mass velocity. This is what it is. And we can say we get this relationship through the center of mass velocity definition. The total mass, when we have a collection of objects, which we call a system, the total mass of that system multiplied by velocity of the center of mass is equal to the total momentum. So if there are many objects with different momentum, P1, P is the symbol we use for momentum. Okay, so we have symbols for each quantity. P is the symbol we use for momentum. So when we have many masses with different momentum, then the total momentum is equal to the total mass multiplied by velocity of the center of mass. Okay, now, so this is after we defined the velocity of the center of mass. Then we defined what we call impulse. So we, by dividing the momentum definition both side by time, we also arrived at an alternative expression for the Newton's second law, which now tells me not the net force is not mass into acceleration. It is correct. It is the Newton's second law. You know, it is originally given as net force is equal to rate of change of momentum. Okay. Right. Now, having defined the net force like that, we can also show an important principle, which is the law of conservation of momentum. And okay, also we introduce another concept, which is called the impulse. So the impulse is, if we apply a force F, okay, more than one force, then we take the net force. And suppose that force is applied for a duration of delta t, the product, the force multiplied by the duration gives us the change in the momentum. Okay, so the impulse is equal to change in the momentum. Okay, so this quantity, the product of the force with the time duration, is called the impulse. That's the definition of impulse. And the symbol we use for impulse is J, the big J. And we can also now write this equation as the impulse is equal to change in the momentum. More impulse mean there will be bigger change in the momentum, and less impulse mean there'll be a smaller change in the momentum. The impulse will have the same unit as the momentum. If the momentum, you know, the unit of momentum is kilogram meter per second, and the impulse, although it seems here because it's Newton and second, that is a unit, but it's also can be shown to be equal to kilogram meter per second. It is equivalent, because if you expand the Newton is actually kilogram meter per second squared, mass into acceleration, and multiply by second, it will give you exactly the same unit as it is for the momentum. Then we said the momentum is defined for a constant force, but if the force is not constant, that is usually the case. The force, when you hit a ball with a bat, the force will, as it contact the ball, it will come to a big value and die down quickly. So because it's remain in contact for a short period of time. So this is what actually happens. So the force is not a constant. So in that case, how do you get the impulse? Easy. We say, if it is a constant force, you can see the impulse is actually the area under the curve, the FT graph. Okay. But if it is not a constant force, again, we will say it is the area under the curve. And you get an average value of the force by getting an average value that will give you exactly the same area if you take the force, the real force. So suppose this area is, I draw it in blue, we will choose the average force such that the area under the average force is exactly equal to the blue area given by the actual force. Okay, so that is where we kind of stopped in the last class. So we will continue to introduce more things now. Again, for a system of object or system, a collection of object. Let's say we got a system with say 4 objects, say mass M1, M2, M3, and M4. The net force on the system, suppose the net force in the sense we will have forces acting between the object. These are internal forces. And we can have forces from coming outside, external forces acting on the some of the object or the object. So net force mean, what is net? Net mean total, sum, okay, the total. So net force, oops, the net force is, what is that? Okay, my gesture. Come on, don't do that. Okay, the net force is equal to, this is the acceleration, right? Because we know the net force is equal to delta P over delta T. For P, I can write mass into velocity of the center of mass. So the net force is equal to total mass into the acceleration of the center of mass. So that's why the concept called center of mass is important. We can say the net force on the system causes the center of mass to accelerate as if all this entire mass, the collection of mass is concentrated, at the center of mass point. All this mass, we can think of it an imaginary point, which is the center of mass, which can be anywhere in the system. So we can say the net force is going to cause the center of mass point to accelerate, given by this Newton's second law, which is now for the entire system. So we have the net force is equal to, we can say it consists of these two kinds of forces, the external force that is coming from outside, and the internal force that is due to interaction between the masses. Now, these internal forces will be coming in pairs, right? We will have equal and opposite, Newton's third law. So if M1, and let me take, there is an internal force between M1 and M2. So if M1 is say attracting M2, or let's say pushing or attracting, there will be an equal and opposite force on M1 from M2 in the opposite direction. So the sum of all the internal force will be 0 because they come in pairs. Yeah, they will cancel each other. The external force is interaction from the external object. The pair will be acting on the external object. We don't care. We only need the net force on what is inside our collection. So the external force is not going to cancel. It is coming from outside. Its pair is not acting on the system. It is acting on something else. So the net force will be simply the sum of all the external force is equal to mass, the total mass of the system, multiplied by acceleration of the center of mass. Right, now we got this equation. Okay, let me rewrite that. External force sum is equal to delta P, P is the total momentum, divided by the time. Now let's say the system that we are considering, we have no external force, or there may be external force, but the sum of these external forces is 0. When the net external force is 0, we have a special result, which is this, because if the left-hand side is 0, the right-hand side should be 0. So that gives us the rate of change of total momentum is 0, time rate. Okay, that means the total momentum is not changing with time. This is what, no, not acceleration, momentum. The total momentum with time doesn't change. So the total momentum is 0. Okay, so what this equation tells us is the law of conservation of linear momentum. You know the meaning of conservation. What is conservation? Does not change. Yes, very good. It doesn't increase or decrease. Whatever the amount that quantity had, say if it is 10, it will be 10 with time. Okay, 1 second it is 10, 2 second it is 10, 1.3 second it is 10. It is continuous. It doesn't change with time. So that is what we are saying. But is it true all the time? No, there is a condition. What is the condition? External, sum of the external forces equal to 0. Okay, some of the internal forces anyway 0. We don't have to mention that. Okay, because of Newton's third law, the internal forces add up to 0. That is no problem. We don't even have, it is always 0. So that means we have to require the sum of the external forces equal to 0. When that happens, I will say the momentum, total momentum. Okay, probably this system that we have, say this mass m1 will have momentum p1, mass m2 will have momentum p2, and so on. So what we are saying now is the p1 and p2 will change. Let's say this is 10, momentum is 10, here the momentum is 8. This may become 12, but what happened, this will become 6. So what is the total momentum before and after? Before, the total momentum is 18, 10 plus 8. Now the total momentum is still 18. So individual momentum may change. We have no problem with that. What we are saying is, if the system has no external, isolated system, no external forces acting on it, then the total momentum will remain constant. So this is the law of conservation of momentum. You can't say it is always valid. What is the condition? Net, there is no external force acting on it. There may be, but they add up to 0. Oops. So we have a question now. Let's read the question and see if we can answer it. An ice skater standing on ice is tossing a water bottle in a vertical direction. Consider the skater and the bottle as a system. Okay. So to answer this question, we have to consider a system. So we say our system is the skater plus the bottle. So let me draw the skater, and she's holding a bottle. So skater plus the bottle is our system. Now this skater is throwing the water bottle up, tossing it up. When she does that, also ignoring friction, is the momentum of the system conserved? Is the question. So we have to immediately remember, okay, we have a system. For this system, can you say the total momentum of the bottle plus the skater, if it is some value before she tossed the bottle up, it is going to be the same after she tossed the bottle up? This is the question. The answer is no. But tell me, why do you say no? What is the condition for conservation of momentum? Feha, can you answer that? What did I told you the condition for the conservation of momentum. What is it? Labib? Anybody there? What is the condition for the conservation of momentum? Rawan? No, I'm asking. I'm not asking you to explain, But I'm asking you to tell me that we had what is called the conservation of momentum, right? No, but we said the conservation of momentum holds only something is satisfied, a certain condition is satisfied. What is that condition? Guys, if you are not listening to me, I'm going to mark all of you absent. That's what I'm going to do. If nobody is responding, that means it doesn't matter whether you're logged in and you are doing something else. I can just easily say you're all absent. I'm sorry, okay? You're all absent. No one is answering me. And don't come and telling me all your excuses. I'm not going to accept any of the excuses. Okay, then tell me, what's the answer? You are talking all rubbish. That means you are not listening to me at all. And tell me, 211433, what is it? Better write your name as well. Can you write your name, please? Who is this? Lian, please. I will have difficulty taking attendance. I can look at your ID number, but you should keep the Lian. Right. So someone tell me the correct answer. Otherwise, you're all going to be in trouble. Fatima? What is the condition for a system to conserve its momentum? Okay, look at this slide and tell me. Yeah, thank you, Kazi. Yes, it is. Yeah, there it is. I told you the rate of change of momentum is zero only when external force is zero, because the equation is net external force is equal to rate of change of total momentum. That's the answer. The answer is, condition is the net external force is zero. So now let's come back to this question. So ice skater standing on ice, tossing a water bottle in vertical direction, and considering the skater and the water bottle as our system, can you say the momentum of this system is conserved? So all you have to do is to see whether the net force is zero or not. If the net force is zero, we can say it is conserved. If it is not zero, we will say it is not conserved. Okay, let me go to the answer, choices. Let me look at the choice number one. You say, yes, it is conserved because the momentum, any system is always conserved. Do you think this is a correct statement? Is it? No. So A is out. No, nobody said it is always conserved, right? Only certain conditions are met. So A is out. B, yes, because the net external force is equal to zero. Yeah, if it is true, then the answer is yes. But do you think the net external force is equal to zero? I don't think so. I will explain that. Okay, but let me go through the other answers as well. C, no, because the net external force is not zero. So it could be either B or C. I know it is C, but we have to explain that. Anyway, let me look at the choice D. No, because the momentum is never conserved. I mean, no. So there are times when the momentum is conserved, right? So that is why we cannot choose D. So it's either B or C. It is actually C. This is the explanation. When the skater throw the water bottle, before throwing, as he stand, okay, we have to look at the forces. What are the external forces on this system? Earth is an external guy. So because Earth is not part of the system, right? Because it is the man plus the bottle is our system. So Earth is, the force from the Earth is an external force, the weight of the man. So let me call it big mg. That is an external force. So there is an external force. But that external force is balanced by The other external force, the normal force from the floor on the man. That's why he's not moving vertically. Okay. So, okay, we are safe because there are only two external forces. The force of flow on the man vertically up. There may be friction, but we are ignoring the friction, but that's a horizontal force. Okay. So we have only two external forces. The other forces from the hand, from the man's hand on the bottle and the bottle on the man, they are internal forces. They will cancel each other. So the only external force is mg and the normal force from the floor on the man. When he is not throwing, as standing still, they are equal. So external force is 0. But the moment he tosses it up, what happens then? As the skater tosses the bottle, she presses on the ice floor with greater force than the total weight. When she tosses it up, the normal force that she exerting on the floor will be greater than the weight. That means the normal force from the floor on the skater will be greater than the weight. So there is a net force because N is not equal to mg anymore when we start throwing it up vertically up. Okay. So that's why C is the correct answer. No, because the net external are not 0, and this is the explanation why it is not 0 at the moment he throws it up. Okay, right. So now we have a continuation, but with a small difference. The same problem, ice skater standing on ice, same scenario, tossing a water bottle, but in a horizontal direction instead of saying vertical direction. The previous case, it is not conserved, but probably it is conserved in the horizontal direction because we are ignoring friction. But he didn't say that ignoring friction, right? Ignore friction, but the question is in the vertical direction, it is not conserved. Therefore, in general, it's not conserved. But in this question now, is asking whether it is conserved in the horizontal direction. This is the question. Okay. Yeah, he's throwing in the horizontal direction. The bottle is being thrown in the horizontal direction. So it is thrown like this. We apply a force, so it is thrown in the horizontal direction. So now, can we say, okay, we can separate direction, okay? We can say in certain direction momentum is conserved, in some other direction is momentum is not conserved. Suppose in a given direction the net force is 0, in that particular direction the net force is 0, then we can say in that direction the total momentum in that direction is equal to 0. So we can take direction separately and say whether it is conserved or not conserved in that particular direction. So this is why this question is a different question, because now he is asking, I'm not talking about the in general, but I want you to tell me whether it is conserved in the horizontal direction. Now, what do you think the answer now? Yes, we have no external horizontal force because we are ignoring the friction. And of course, we are ignoring the air resistance also. Okay, that is anyway very small. We can ignore safely. But we are ignoring the friction as well. That means there can't be any external force in the horizontal direction. This force that he is pushing on the bottle is an internal force. When you push the bottle to the right, bottle will push the man to the left. They are internal forces. They cancel it. That doesn't matter. Internal forces, there can be any amount of internal force. They come in pairs, they will cancel each other. You only have to worry about external forces. So in the horizontal direction, there are no external forces. So in the horizontal direction, the momentum will be conserved. Okay, so that's the answer. So we have four choices again. So you know the answer is what? B. Equal to, yes, yeah. Because A is not the answer because it's the wrong reason. Yeah, not, you can't say always conserved. Okay, so B is the correct answer. Right. So no external force in the horizontal direction, assuming 0 friction between the skin. Now we have a question that we have to solve. Yes, Saida, thank you. Ice skater of mass 45 kilogram initially standing on ice. Okay, again, now it's a numerical problem we have to solve. Okay, and she tosses 1.2 kilogram water bottle at a speed of 14 meters per second at an angle of 34 degrees with respect to the ground. So there's a picture in the next slide. So I will go there. And the question is, what is the recoil? I mean, when you throw that, the skater will move backward, you know, right? If you're in an ice where there's no friction, it's zero friction or almost zero friction, you throw something, you will go in the opposite direction. Why? To conserve linear momentum. That's why that happened, okay? Because no friction mean in the horizontal direction, there is no net external force. So now suddenly you are giving a momentum to something part of the system. The bottle has a momentum. Before the momentum was zero because the bottle is at zero velocity. The skater is at zero velocity. The total momentum is zero. Now suddenly you throw the bottle in one direction. Okay, all internal forces horizontally. So the bottle has a momentum, a positive momentum, but you can't allow it because according to the conservation of momentum, which is valid, which holds here in the horizontal direction, the total momentum should be zero. So if the bottle suddenly get a positive momentum, the skater should get a negative momentum to make that zero, total momentum zero. That's what happened. So now we have a tools, the physics principle to solve some practical problem. Okay, well, if we consider this a practical thing, okay, well, the everyday problem. So let's see how it is done. So this is the skater, she's throwing the bottle and the bottle has a speed, let's say it's given to us 14 meters per second, but she is not throwing vertically up or horizontally in between. So it means she will have a horizontal velocity, which is 14 cosine theta. Theta is given 34. Vertical velocity will be 14 sine 34. Okay, we are only interested in the x momentum, horizontal momentum, because we can apply the conservation of momentum only in the x direction. So let's see what is done. So what is our equation is this. Do you read this equation, what it says? Sigma mean sum, right? Total momentum, I mean initial, F mean final. So this is the conservation of momentum. The total momentum before, total momentum after, because we are requiring what is the event throwing the bottle. So before throwing the bottle, suppose there is a certain momentum, total momentum for the system, that momentum should continue to be even after throwing the bottle. So before throwing the bottle, the total momentum is 0 plus 0, because the bottle is zero momentum, the skater is zero momentum. So total momentum before throwing 0 plus 0, 0. So this is 0. Total momentum after it is being thrown, let's put that in. It is the momentum of the water bottle in the x direction. We are only applying this in the x direction, by the way. We are only applying in the x direction. Can we apply it in the y direction? No. In the y direction, you know, because the same what we answered before, the net force is not zero because you're pushing harder on the floor. So the normal force on you will be greater than the weight. So it is not balanced in the vertical direction. But in the horizontal direction, there is no friction. The total momentum is conserved. So we now substitute for these things. This is what? This is the bottle mass multiplied by bottle velocity in the x direction. This is the skater mass multiplied by skater velocity in the x direction. So that is the total momentum. So we say 0. Now this is, we substitute. Now you do some algebra here. So I'm going to show you what happened. I can bring it to the left side. So it will become minus mbvbx is equal to msvsx. So we are after this, right? The skater's velocity. Everything else is given. So I can get this. If I take it to this side, so this is what we get. Now, once you have the formula with the unknown as the subject, now in matter of substitution, MB is given 1.2 kilogram, and the X component of the initial velocity of the bottle is 14 into cosine 34. Because that's the X component. Divide by mass of the skater is 45 kilogram, and you get this answer. We get a negative answer. Does it make sense that we are getting a negative answer? because we are taking the bottle's velocity as the positive side. So the scalar will move in the opposite direction to the bottle velocity, which we took. We took because we substituted positive value for bottle velocity, right? So we are taking that is a positive direction. So we are getting a negative answer for the scalar velocity. So we know what's going on. The scalar will be moving in the opposite direction to the bottles, the direction in which we throw the bottle. Okay. Right, now we come to collision. Now you know what collision means? Hitting, right? Yeah, like car accident, two cars. So let me just, before I come to this, let me discuss cars so that you'll probably understand very quickly what is collision mean. Let's say this car has a momentum P1 and this car has a momentum P2, and somehow there is a collision. Okay, then after collision, the momentum will change, right? This becomes a P1 become P1 dash, car 2, after collision, let's say it's become P2 dash. Now, can I say as a general principle, the momentum is conserved for this collision? The condition is net. Yeah, what is the condition for conservation of momentum? Net force is 0. The net force acting on the system is 0. If that condition is satisfied, the total momentum does not change. It is before and after, they should be equal. The condition is the net external force. Well, yeah, if there is no friction, okay, in the horizontal direction, there's no. In the vertical direction, let's say the forces balance, okay, so then in the horizontal direction, there is no friction. We can assume is, in a collision, momentum is conserved. But I'm going to say, even if there is some friction, I can approximately maintain in any collision, momentum is conserved, provided we are talking about short duration of the collision. The collision happen, usually the collision lasts like fraction of a second, right? So what I'm saying now is I'm going to make a general statement, which is in any collision, irrespective of, we are not even talking about the net force equal to 0 or not. The total momentum is conserved, provided it happens in a very short period of time. So we can ignore the external forces. Because when the collision occurs, there are going to be big force between these two cars, right? Because those forces of collision is great, like 10,000 Newton or 100,000 Newton, big force. But the weight of the car or friction, okay, this friction is going to be very small compared to those internal forces that happen when they collide with each other. So what is significant is the effect
Doctor, we can't hear you.
Yeah, can you hear me now? Sorry, I disconnected for some reason. Yeah, thank you. Right. So where was I? Yeah. We are looking at collision. Okay. So I'm going to make a general statement. Forget about what I said so far. Just we say that in any collision, we are only talking about right before the collision, right after the collision. We are not going to wait too long, like too long. We are not going to watch it for a long time. Right after the collision and right before the collision, if you take the total momentum, they should be the same. That's what we are telling. So in any collision, momentum is conserved. So when we have a collision problem, we can apply the conservation of momentum. So here we have an example, what we call inelastic, perfectly inelastic collision. Okay, so that I have to qualify that. We have two kinds of collision, elastic collision and inelastic collision. We will not bother too much about that two types. So elastic collision mean energy is conserved as well. But here we are only talking about momentum is conserved always, okay? Whether it is elastic or inelastic, momentum is conserved. Perfectly inelastic collision mean when these two objects that are colliding, if they stick together, combine, glue, entangle, okay? If they suppose they become combined together, we call it perfectly inelastic collision. So we have a question where after the collision, the two objects merge, combine together, and we are asked to find the final velocity of this combined object given the initial velocities of the object. So let's look at the picture of this question. But with the additional simplification, we have two objects, one object having a velocity v1i, one v1 stand for the mass 1, and I stand for initial, before collision. And m2, the velocity is v2i. So we are making a simplification. We are going to assume the m2 is at rest. Okay, just to make it simple, easy calculation, m2 is at rest. And after collision, they combine. So now we have only one object. For some reason, they become just stick together, glued together, combined. So the velocity is just one velocity. I mean, there is no need to say velocity of 1 and velocity of 2 because they both move with the same velocity glued together. So let me say VF. If we know M1, M2, and V1i and V2i, of course, V2i is given as 0. Can I find the final velocity after the collision? Yeah, because we have an equation now, the conservation of momentum. So let's see how it is done. So that's a question. First question is determine the final velocity. And there are two more questions. I will come to that. Let me do the first question, A. So I will skip that. See, this is what we are going to apply. The net momentum before collision is equal to the net momentum after the collision. Right. What is the net momentum before collision? Well, momentum of the first particle, which is m1 v1i, it's a one dimension, everything moving in the x-axis only, plus the momentum of the second one is 0 because we say v2i is equal to 0. I mean, it's a special example where one of the object is at rest, the other one is coming with the speed. Then after collision, this is the total momentum. There is only one object having a mass of the sum of the two, m1 plus m2, and its velocity, which we say we don't know. We are going to determine if possible from, well, it's very clear, right? So I can solve for that. I can bring it to this side. So I can say Vf is equal to m1 divided by m1 plus m2 multiplied by the v1i, initial velocity of the mass 1. So we are saying we know V1i, we know M1 and M2. So we can find the final velocity of the combined object. So that's it. Okay, so we got an expression. We don't have numbers. Suppose M1, they are giving the numbers like 10 kilogram, 12 kilogram. We can put in there. And if we know the initial speed of the mass M1, we can find the final velocity of this combined object. But we got some more question. We got the answer to A as an expression, not a number. what happen when, see, one of this, the one that is coming is a big, heavy, and the one here, M2, is less heavy, massive. You know, right, what will happen? You can guess. So that is, this guy is coming with 10 meter per second. It's a big guy, say 1,000 kilogram. And this is a small guy, say 1 kilogram. And he is at rest, zero velocity. After collision, what do you think will happen? They will combine, okay? We are assuming combine. What about the velocity of the combined object? Will it be less than 10 meter per second? Okay, say this is a big car, okay, coming with 10 meter per second. And this is a small car. Stop. It hits. After collision, you think it will stop? It will move. So I'm asking, what is that final velocity? I mean, I want to compare to this 10 meter per second. Is it going to be, I mean, much less or almost 10 meter per second, maybe 9.9? Yeah, it will not change that much, right? So you can just kind of common sense. But can you do it with your physics knowledge, conservation of momentum? Let's see. See, the answer that question, what happened if the one that is coming has a big mass compared to the one that is stopped? See, if this, let's say this is 1,000 kilogram, and this is only 1 kilogram. This is still almost 1, right? 1,000 divided by 1,001, still it is 1. Because, you know, as if it doesn't matter because very small. We can just ignore M2 because the effect on the M1 plus M2 from M2 is negligible. So it is like VF is still equal to the V1 initial. Okay, so we can say, kind of taking the limit when this M1 is much greater than M2, we can ignore this guy. So the ratio VF over V1I is equal to 1. Omar. Did you attend? You're listening? Can you tell me what you learned? No. I don't need proof of your attendance. I need proof of your really listening to me.
Doctor, I have a question.
Sure, go ahead, please.
Why we said it's 1?
Okay, all right. Okay, let me clear this and show that.
Okay.
Right. Let's say this is 1,000. Well, the condition is M1 is much greater than M2. Let's say this is 1. Okay, so this is 1,000. Now, what is this value? 1,000 divided by 1,001. Take your calculator and tell me what it is equal to. Sadim?
It's the same.
No. Tell me.
No, sorry, 0.9.
It's equal to what? 0.9. No, tell me. So give me other digit. Okay, 9.
Yeah, it's 1.
How many
9?
3.
3. Yeah, 3.
3, 9, and something, right?
Yeah.
Isn't it almost equal to 1, right? Isn't it?
Yes.
Yeah.
Yes.
So suppose even let me take this is big difference between M1 and M2. Let's say it is say 10,000 kilogram or 100,000 kilogram. 100,000 divided by 100,001, you will find it is even closer to 1. It will be
Yes.
0.9999999 and something. So that's what we are saying here. If M1 is much greater than M2, I can kind of ignore this M2. And
we
say
put only 1.
Yeah, it is. That means the final velocity is almost equal to the initial velocity of M1. Okay.
Yeah. Okay. Thank you.
Welcome. Right. So there is another question. See, what the other what if this guy, this is the M1 is big, right? Let's say M1 who is coming with 10 meter per second, and the one that is stopped is M2 is very big. So now this is 1 kilogram and this is 1000 kilogram. What do you think? And forget about the physics. What do you think will happen? Now they combine. This small guy comes with a big speed and hit the big guy, and they stick glue into the big guy. What will be the velocity after collision of the combined object? No, I mean, it's 10 meter per second, right? Now the big guy has a speed of 10 meter per second. He's hitting the small guy. He's hitting the big guy. They combine. Now, what do you think the speed of this combined object comparing to 10 meter per second? Will it be less than 10 meter per second, much less, or much greater, or equal? This guy will stop him, right? I mean, think in the scenario. Now, let's say there is a very fit, heavy guy, and you go and hit him. Will you be able to move him? No, he will be almost in the same place still. No, let's say you catch him, you hold him. So you are becoming combined now. Will you be able to push him? He will have only a very small velocity. He will not be affected that much. So can you get that answer from our equation? If M1 is much, much smaller than M2, now what happened? This is very big. So this will be, say, 100,001. Say if it is big, 100,001. This is only 1. 1 over 100,001 is almost 0. So the speed of the combined object will be approximately 0. Okay. So we getting the result that you can imagine. Okay, we can get it from the laws.